All right, so two other colligative properties that come from this idea of vapor pressure lowering are what we call boiling point elevation and freezing point depression. So the properties that we're looking at are the boiling point of the solution versus the pure solvent and the freezing point of the solution versus the pure solvent. So if we think about what lowering the vapor pressure does, right? It happens at all temperatures, right? So the vapor pressure gets pulled down at all temperatures. So that means the pressure is lower for the solution versus the solvent at all temperatures. So if we put this in terms of a phase diagram, what we see is the vapor pressure curve, and therefore the fusion curve as well. Everything gets drugged down, right? The pressure gets drugged down. So because of the shape of these curves, right, it causes the boiling point to shift to the right or toward higher temperatures, right? The boiling point gets higher, and it causes the freezing point to shift to the left or to lower temperature. So this vapor pressure lowering causes changes to the boiling point and to the freezing point. And we recall these boiling point elevation, indicating that the boiling point is elevated for the solution. And we have freezing point depression, indicating that the freezing point is lower for the solution. Okay, so let's look at each of these individually, and what we'll see is basically they operate the same way, but in opposite directions. So the first thing is we can say that the boiling point of a solution is going to be higher than the boiling point of the pure solvent. Now, we have to make a condition here that for this kind of problem, we're dealing with a non-volatile solute. If we start introducing solutes that also boil, well, then it becomes increasingly complex to try to parse out the different pieces here. So we're only going to look at problems where we have a non-volatile solute, meaning ideal conditions under Rhodes' law, right? So only the solvent is volatile. So the difference in boiling point of the solution and the pure solvent is written as delta TB, or the change in the boiling point, and it's directly proportional to the molality. So notice here, we're using our concentration unit as molality. Now, as you might recall, molality is mass-based, right? And we commented that mass-based concentration unit is often used when we think about changing temperatures. And so we're going to see these boiling point and freezing point changes. We're going to use a mass-based concentration unit, or molality. So we have our change in boiling point, right, which is, this is always calculated by taking the solution minus the solvent, right? Because the solution is going to be higher, something lower, we're going to get a positive change. It equals the molality times, again, a proportionality constant. And this particular proportionality constant is called the boiling point elevation constant. It's abbreviated KB, or capital KB. And with all proportionality constant, it has strange units. So this is going to be solvent-based, so each solvent will have its own value of KB. And the units are degrees Celsius per molality. So degrees Celsius per molality. And again, this allows the units to cancel out so that we get our change in change in boiling point in units of degrees Celsius. So of course, you're going to find tables of these constants, and you're going to plug them in. Now, freezing point depression, notice the equation is identical. The big difference here is to calculate the delta TF, or the change in freezing point. since the freezing point of the solution is always going to be lower than the freezing point of the solvent, we do the solvent minus the solution. So again, our change in freezing point is a positive change, because the freezing point of the solvent is always going to be higher than the freezing point of the solution. And again, it's directly proportional, in this case, to the molality. Right? So again, we use this mass-based units. And now instead of having a boiling point constant, we have what's called a freezing point constant, which again has the same units and again is linked to the solvent. So two closely related phenomenon. Now, these seem like they could be sort of obscure ideas, but these are things that we actually experience quite often, or at least the phenomenon of them quite often. So you see the picture here putting antifreeze in your car engine. Now, what's the point of using antifreeze? Well, it's to take advantage of these particular colligative properties. So in your radiator in your car, you could run pure water. And that's how it was done for, a long time, until the advent of antifreezes. Now, all we're doing when we make an antifreeze is we're making a solution, right? And what is that solution? Well, it's going to change the properties of the liquid running through our radiator. It's going to make that liquid harder to boil, right? It's going to raise the boiling point compared to water, and it's going to lower the freezing point. So it's going to make it harder to overheat our engine or to boil the liquid in our radiator, right? So you've seen in old movies or old pictures, right? Cars sitting on the side of the road, steam coming out of the radiator because, you started to vaporize the fluid running through the radiator, right? Well, this prevents that or makes it much harder to do. It also makes it harder to freeze that solution running through your radiator, which can happen in, really cold weather. You come out and your thing is set overnight. If it's water, right? If it gets below freezing outside, the water running through your lines in your radiator would freeze. Right? That makes it really hard for your car to run, right? And you wouldn't be able to until you thawed out that radiator fluid. But using antifreeze, right, creating a solution, takes advantage of these ideas and allows us to have a solution running through our radiator that doesn't freeze when it's really cold and doesn't boil when it's really hot. Now, based on where we live and how cold it gets, or potentially how hot it gets, we can use different concentrations of solution, right? The higher the concentration, the more it's going to protect, right? The higher and lower temperatures it's going to protect against. Okay, so I just throw this chart in there just to show you that these constants are solvent-based. You do not have to memorize them. The ones that we will most often use and the ones that you'll become most familiar with are the values for water. Now, of course, you should know the normal freezing and boiling points of water that you're comparing to, right? A freezing point of 0, boiling point of 100. So for water, the Kf is 1.86 degrees Celsius per molal, and the Kb is 0.512. Now, a general observation, right, is that notice the effect on the boiling is typically lower than the effect on the freezing. So you can see here, there's a 1.86, right? Now remember, this is going to be multiplied by the concentration. So the same concentration solution, you're going to have a bigger effect on the freezing point than you will on the boiling point. So for water, it's almost a factor of 3.5 or 4. And other things, it's closer. But typically, there's less of an effect on boiling point than there is on freezing point. But, we don't need to necessarily worry about that. We just pull our constants and we do our calculations. Now, I'm not going to go into these in detail, but I just wanted to point out a couple of other places where we take advantage of these. Now, I will post a video up in on Talon that you can go watch that'll talk about these and these supplemental videos. And those of you who have me for Chem 1, you're familiar with these videos that I will assign in the weekly assignments for you to watch that will sort of give you different perspectives from some of the topics that we talk about, either reiterating them, having sample problems, or just giving you some other perspective. And of course, I expect you to watch these on sort of an ongoing basis for each chapter. So when we talk about how it prevents freezing in our cars, right, antifreeze, well, different plants and animals also can take advantage of these. So for example, evergreen trees, right, they hold on to their needles in the winter because they have the ability to flood the cells in those needles with things like glucose. And by upping the concentration of glucose, you can make it harder for that intercellular tissue, right, to freeze. And it's that freezing of the tissues, of the interstitial fluids, that cause, the leaves to die and so forth, right? Now, this is not the only way that they do it, but this is one mechanism that they use, right? There's other ways that evergreens do, or other features that evergreens have that help maintain those green leaves. But this is one thing, right? They keep those needles from freezing by upping the concentration of glucose in the cells. In the book, you might see a little, if you read through the book, they have a little discussion of a frog that operates under the similar situations, right? So since a frog can't regulate its body temperature, right, it's highly susceptible to, freezing, right, if it's left out in the open. Well, this particular frog can basically partially freeze, but flood its tissues with glucose to keep its cellular fluids from freezing. And then when it warms up, it comes back from that hibernation, but its cellular tissues haven't frozen, so it stays alive, right? Imagine what would happen if they did freeze, right? It would kill it because, remember, these are water-based. When it freezes, right, the ice, it expands, that would burst the tissues, and when it thawed, you would just be left with mush, right? Think about what happens if you have something like lettuce and it freezes. It gets too cold in the refrigerator and freezes, and then it thaws out. It's slimy and nasty because you've broken all those cell walls down. Now, another sort of obvious place where we take advantage of this is de-icing the road, or de-icing airplanes and these kind of things. We add materials that get incorporated into the water and keep it from freezing, right? So we put salt on the roads because as that ice starts to melt just a little bit, that salt dissolves, and now you have salt water instead of pure water, and that salt water is harder to freeze, and so that water doesn't refreeze on the roads, and so we prevent this formation of re-icing overnight, right, when it gets cold. So different applications where we actually see taking advantage of these particular colligative properties. Now, the last colligative property that I want to talk about is something that is a bit more obscure, and this is called osmotic pressure. So this is related to osmosis, right? Something that we talked about at the beginning of the chapter, where we have the flow of solvent, right, from a solution of low concentration to a solution of higher concentration. And remember, the whole point of that is to try to equalize the concentration, that idea of spontaneous mixing. And this flow is occurring through some semi-permeable membrane. So this could be a cell wall or some sort of cellular tissue in the body, Or it could be in a lab, we can have some sort of artificial semi-permeable membrane, right, that allows the solvent, likely like water, but not the solute, to flow through it. Now, this flow is natural, right? It's going to occur. If we want to stop that flow, we can apply pressure to the high concentration side of the solution, right? And we can prevent osmosis. And the osmotic pressure is the pressure necessary to stop osmosis. So to stop this flow of solvent. And so the osmotic pressure, represented by capital Pi, is directly proportional to the concentration of the solution. And in this particular equation, we quote that we use units of molarity. And so the osmotic pressure is equal to the molarity. Now notice the presence of R, right? Our gas constant, right? You might remember it from the ideal gas law. Right? Remember, we're working with pressure here, so, right, we're going to have the ideal gas law constant, and this relates pressure, volume, moles, and temperature. So we have a temperature term here, and unlike every place else that we've worked with in this chapter, this particular equation uses Kelvin temperature like we did with the gas laws, right? So typically when we're dealing with gases, equations with gases that have temperature in them, we're going to use Kelvin because of the units of this gas law, or excuse me, of the gas constant here. So osmotic pressure is equal to the molarity times the gas constant times the temperature. So what you can see is that the higher the concentration of our solution, the more pressure it takes to stop the flow. So in other words, the bigger the difference between those two concentrations, the stronger the incentive is for osmosis to occur, and the harder it is to stop it. So the more pressure we have to apply. And this is also dependent on temperature, right? Higher temperature is going to lead to higher osmotic pressure. So let's look at some pictures. So initially, we have this setup where we have our high concentration solution here. We have our low concentration solution here. Right? So we have our semi-permeable membrane. So right, we're going to flow from low concentration to high concentration. Right? So the net effect is to try to dilute this side to try to make these closer to each other. So solvent's going to flow like this. So we're going to see this level go up, this level go down, right? Which is what we see. The difference in height, so if we let this go, the difference in the two sides of this column represent the osmotic pressure, right? So the height difference here gives us a measure of the pressure that is necessary to stop this flow. So if I want to stop this flow, I need to apply pressure, again, and I need to apply it to this side, right? Because since the flow is going this way, the osmosis, I need to apply the pressure here to stop it. And the pressure needs to be equal or greater than the pressure that we would be equivalent to this height difference. Okay? So this is the idea of osmotic pressure. Now, before I move on, you might be familiar with something called reverse osmosis, right, as a filtration system. So what that is essentially is we don't just stop osmosis, we cause the flow to be opposite of osmosis. So we apply a pressure much larger than the osmotic pressure, which actually makes the flow go this way instead of the natural way. So we cause the water to flow from the more concentrated solution to the more dilute solution. So what we end up with is essentially just solute over here and pure water over here, right? So it's a way to purify this water here. So we call that reverse osmosis filtration. Okay, so the very beginning of this section, I talked about the fact that colligative properties are based on the number of particles. And so that means we need to treat something like an ionic compound different because it breaks into multiple particles when it dissolves. So we need to take this into account if we are calculating a colligative property of an ionic material, right? If what we're dissolving is an ionic material, our solute is ionic versus molecular. And this is done by using something called the Van 't Hoff factor, which is represented by script lowercase I. Now, most often, we will use what's called the theoretical Van 't Hoff factor. And the theoretical Van 't Hoff factor is basically just the number of ions that an ionic compound will generate. So, for something like sodium chloride, right? Remember I said that 1 mole of sodium chloride generates 2 moles of ions, right? 1 sodium, 1 chloride. So basically we're going to look at the formula and we're going to generate the Van 't Hoff factor. So I here would be equal to 2. Now if I had something like MgCl2, right? This is going to generate 3 ions, right? Each unit here for my formula is going to generate 1 magnesium ion, 2 chloride ions. And so this would have a Van 't Hoff factor of 3. So a theoretical Van 't Hoff. And this is typically what we'll use. Now, there is also something called a measured Van 't Hoff factor, which is what it actually is in solution. And typically, it's going to be lower than the theoretical because we don't get perfect separation, right? We get what we call ion pairing, where some of the ions in solution will group back together. And so you don't actually get that theoretical number of particles. Now, the only reason you would use a measured Van 't Hoff factor is if you were given a measured Van 't Hoff factor. So if you're not given a measured Van 't Hoff factor, you're just expected to use the theoretical value. Now, the thing to keep in mind, right, is that by using the theoretical value, you're going to get changes in temperature that are perhaps higher than what you would actually observe. So you're going to calculate, say, a freezing point. You're going to calculate how much the freezing point changes, but in reality, it may not quite change that much because your I value is lower than what you expect. And let's look at the equations, and that might make a little more sense. So if we take our 3 of our equations, so we'll look at vapor pressure here in a second, but if we take our boiling point elevation, freezing point depression, osmotic pressure, the Van 't Hoff factor is simply a multiplier. So if we have a molecular compound, right, I equals 1, right, for a molecular compound, like sugar or ethylene glycol, anything, right, that is molecular, right? The Van 't Hoff factor is 1. So it's just the normal formula. But if we have an ionic compound, then we're going to plug in our Van 't Hoff factor, and you can see we're going to see the effect. So if Van 't Hoff factor is 2, which means we have twice the number of particles, right, we're going to have twice the effect. So the boiling point is going to change by twice of what we think it would, and so forth. So we're going to get much bigger effects with ionic compounds, theoretically, than we will with molecular compounds. And so you can look at, say, sodium chloride, for example, right? Theoretical Van 't Hoff factor is 2, measured is 1.9. So for a lot of materials, there's not a lot of difference. Now, you will find examples where, there is quite a large difference, and this would be found experimentally. Right? But, you are just expected to use the theoretical value unless you're given a measured value. And if you're given it, use it. Now, it's really easy to take this into account for these three. Now, vapor pressure, it's a little trickier. This is going, for vapor pressure, it's going to be taken effect by looking at the mole fraction of solute versus solvent. Right? So when we calculate the moles of solute, we're going to look at the moles of solute particles. So essentially, what having a Van Hoff factor is going to raise the mole fraction of solute, because now we have more particles. So really what we're looking at is moles of particles. And so if it's, if 1 mole of molecules equals 1 mole of particles, well then, moles of compound equal moles of particles. But if I generate more particles, then I need to take that into account. So the way we take this into account is we calculate moles of particles. And so what that's for an ionic compound is going to raise our mole fraction of solute, which is then going to lower the mole fraction of solvent. And then if that's lower, then we'll see the corresponding effect on our vapor pressure. Okay? So we don't directly take it into account in Roth's law. It gets taken into account in the background by making sure that we correctly calculate the moles of solute, or the moles of solute particles in solution. Okay, so the last part of this is we're going to do a few more problems using some of these different colligative properties.